Hello, my name is Tony Lentz with FCT Assembly, and this is a video presentation of Size Matters, the effects of solder powder size on solder paste performance. First, I'll give you a brief introduction on the topic that we did some research on. We'll talk a little bit about how solder powder size affects printing and reactivity of solder pastes. And then I'll go into some detail on the test methods that we use to evaluate how solder powder size affects paste performance. I've got a lot of data to share, but some of the data has been removed in order to keep this presentation under 30 minutes. But all of the data is included in the paper version of this. And if you have any questions, of course, you can get in touch with me. And then at the end, I'll have a summary of the data and some conclusions that we can draw from the data. And if you have any questions, again, you can email me or call me at the contact information that will be at the end of the presentation. So size matters in everyday life in many different ways. This is a picture of an antibody, which is microscopically small, but it has a huge effect on the health and well-being of people. I think people with smaller hands do a better job of speed texting. I know I struggle with that. I'm not a very fast texter. I got to backspace a lot and correct words. And certainly in football, you want bigger people to play on the offensive and defensive line. Obviously, if you had small people playing in those positions, they'd probably just get steamrolled and the quarterback would get sacked. And of course, nobody wants a small cup of coffee. I know I certainly don't. In the world of solder powder, size also matters. In this study, we studied the effects of type 3 through type 6 solder powders in two different types of solder paste. And those size ranges range from 45 microns for type 3 all the way down to 5 microns with type 6 solder powder. Solder powder size certainly affects printability. In fact, most people think about switching solder powder sizes when they reach an aperture size which is too small for the current size of powder they're using. For example, if they're using type 3 solder paste and then you start, say, placing a lot of 01005 type components, at that point you may decide to switch to using type 4 solder paste or even type 5 in some cases in order to get good printability. If we take a look at the 5-ball rule from the stencil design guideline, which simply says that you need 5 particles of solder powder across the narrowest dimension of an aperture in order to achieve good printability, then we can derive these minimum aperture sizes from the IPC size ranges for these solder powders. So here I have type 3 through type 6 solder powder sizes, the size range in microns, the size range in mils, and then if you use the largest size of the size range in mils, multiply that by 5 particles. These are the minimum aperture sizes that you could potentially print through. So with type 3 solder paste, you could potentially print through a 9 mil aperture. With type 4, 7.5 mils might be the minimum size. With type 5, that goes down to 5 mils, and then type 6 would be as small as 3 mils. And these aperture sizes roughly correspond to these sizes of chip components shown on the right. So type 3 could potentially be used for 0402 components. Type 4 for 0201 type components, type 5 for 01005s, and then type 6 would certainly be used for these microscopic 008, 004 or smaller components. Now, of course, these are theoretical or recommended rules for aperture design. Solder powder size also affects reactivity, which is because of the surface area on the solder powder. As the solder powder size becomes smaller, the surface area gets much larger. And here's a table where I went through the math and calculated the surface area of these different types of solder powder. If you had the same mass of each type of solder powder, what would the surface area be? So here's the surface areas that I calculated. For type 3, it's about 23 square meters for 1 kilogram of powder. For type 4, it's about 28. Type 5 is 40, and type 6 is 80. So there's a big jump, obviously, from type 4 to 5, and then another big jump from 5 to 6. Now I went ahead and normalized those surface areas to compare them to type 3, and this column on the right is the amount of surface area that these powder types have that are greater than type 3. So for example, type 4 has 21% more surface area than type 3 solder powder. Type 5 has 75% more surface area than Type 3. Type 6 has 350% more surface area than Type 3. And that's graphically shown by these blocks at the right. So you can see from Type 3 to Type 4, there's a small increase in surface area. Type 3 to Type 5, there's a big jump. And then from Type 3 to Type 6, it's a huge jump, 3.5 times more surface area with Type 6. Surface area definitely affects reactivity. So I did a little experiment in the lab to show an example of this. I took granulated sugar and put it in the bottom of a beaker and then added a certain amount of water and mixed for a minute. The granulated sugar dissolved completely in that 1 minute mix time. I took the same mass in a cube form, added the same amount of water, mixed for a minute, and after that 1 minute mix, there's still some sugar left here in the bottom of the beaker that did not dissolve completely. And that's because the surface area of the granulated sugar is much higher than the cube of sugar, so it dissolves much more quickly. Well, the same thing happens with solder paste. As you go to smaller solder powder sizes, the higher surface area will react more quickly and more completely with the flux medium, and it'll react with air when it's open to the air. It'll react with heat in the reflow oven more quickly. So you've got to be aware that smaller solder powder sizes can lead to some benefits and some issues with solder pastes. Here are some of the issues that smaller solder powder sizes are susceptible to. First, you've got random solder balling, where you've got just microscopic solder balls kind of floating around in the flux pool. Graping is a potential issue with smaller powder sizes. And then aging, like stencil life or shelf life, can be affected by smaller solder powders. So here's what fresh paste might look like: smooth, wet, and creamy. And then after air exposure for several hours, it can turn dull and get thicker and may not be as easy to print. Here are the things that we studied with regards to solder powder size and how it affects solder paste performance. We studied shelf life and stencil life. We took a look at viscosity, slump, and solder balling performance per IPC standard. We measured tack force over time to see how stable the pastes were in terms of tack. Did they hold their tack over time when open to the air or not? We also did print and pause testing to measure printability. And then we did some reflow testing and measured wetting, graping, and voiding. And then we also did some stability or reactivity tests with the solder paste and then measured performance after that was done. Here's our test methodology that we used to run all these experiments. First of all, we used this test board, which is called a PR test board. Here we have printed area ratio limit patterns, which range from 0.30 up to 0.50 area ratio on the stencil, which are extremely small area ratios. And we did that in order to challenge the printability of these solder pastes. Here we have BGA arrays, which are 0.4 millimeter pitch, and those are good for measuring transfer efficiency and repeatability, like coefficient of variation and whatnot of solder paste printing. Then we also measured wetting or spread percentage, graping, and then random solder balling using these patterns. And then we can measure voiding using these QFN thermal pads on this test board. Here are the 8 different solder pastes that we made for this experiment. Here's the different types of solder powder. Here's the 4 no cleans that we made and the 4 water solubles, and these are the metal concentrations that we chose to use for each solder paste. Now, it's fairly common for us to reduce metal concentration as you go to smaller powder sizes. That's typical of most solder paste suppliers, and that's done intentionally in order to compensate for that increase in surface area that the powder has. So as I showed earlier, the surface area goes up when you go from type 3 to type 4, so therefore we reduce the metal concentration a little bit in order to give the paste the same type of print and reflow characteristics that are desired. The no clean solder paste is classified as an ROL0, and the water soluble that we used is classified as an ORH1. And we intentionally picked these two because they have much different properties and different activity levels, and they show different performance behaviors with these different types of solder powder. All of these solder pastes were made with SAX 305 alloy. Here's how we ran our print and pause testing. First, we printed 5 boards and measured solder paste volumes. Then we reflowed all 5 of those, and we measured our fresh reflow properties off of those boards. Then the paste sat for 1 hour idle on the printer without being moved. And we printed 2 more boards. Those two boards were all sat on the counter for 24 hours, open to the air, and then they were reflowed the following day to try to see what effect that would have on reflow performance. The paste, meanwhile, was still sitting on the printer for another hour. Then we printed two boards and measured solder paste volume. And then we waited for 2 hours and printed more boards and measured volume. Waited for 4 hours and then waited for 16 hours. So the solder paste sat on the printer for 24 hours total time. And then we printed after different lengths of pauses during that period of time. And what we're looking for here is drop in transfer efficiency or major changes after these pauses. We performed reflow testing using this profile, which is a linear ramp to peak type profile. The measured specs on the profile are shown here, and this is a pretty typical SAC 305 profile that we would use for our solder pastes. In terms of reflow, we gathered data on freshly printed boards and the boards that sat open to the air after 24 hours. We measured wetting percentage, solder balling, graping, and voiding. Here's the standard solder paste test that we ran. We ran T-bar spindle and spiral pump viscosities. We ran slump and solder balling per J standard 005 test methods. And then we measured tack force over time. The tack force was measured on freshly printed coupons, and then on coupons that were printed and stored in a humidity chamber at 50% relative humidity for 24, 48, and 72 hours. And what we were looking for there is like a drop in tack force over a period of time. Some solder pastes don't drop at all, and some drop pretty rapidly as you store them open to the air. We also did aging or stability tests. So we sealed the jars of solder paste and put them in an oven at 50°C for 72 hours. Then after that period of time, we measured viscosity, solder balling, tack force, and print and reflow characteristics. The whole idea was to force a shelf life on the solder paste in much a similar way as the forced aging that occurs with our U.S. presidents. Here you can see pictures of our last two presidents before and after they got out of office, and you can tell like their hair went gray. There's, maybe more wrinkles on their face. And that's a highly stressful job. So it's sort of like a pressure cooker that forcibly ages these people. And we were trying to do the same thing with our solder paste by heating it in the oven. Here's the data on the standard solder paste tests that we ran. Here's the T-bar spindle viscosity data. So here's viscosity on the y-axis and the different types of solder powder across the x. The no clean solder pastes are shown as this amber colored curve, and the water solubles are shown in blue. And that'll be consistent throughout this presentation. All the amber or brown colors are no cleans, and the light blue and dark blue colors will be the water solubles. So here you can see the no clean increased in viscosity a little bit from type 3 to type 4, and then it jumped a lot when we went to type 5 and type 6 solder paste. The water soluble, however, had pretty consistent viscosity. Type 3, 4, and 5 were all very similar in terms of viscosity. Type 6 jumped a little, but it's also not as big of a jump as what happened with the no clean. The same trend is true for the spiral pump measured viscosities, although the scale is a little bit different, but the no clean basically went from 1100 up to 1700 with type 6. And the water soluble didn't change as much. It was 2000, 1800, 1800, then 2300. So much less of a change with the water soluble than with the no clean. Here's the solder paste slump results. Here we have the no clean cold and hot slump, and then the water soluble cold and hot slump with the different types of solder powder. So we got a failure with the type 5 water soluble on hot slump, and then failures with the type 6 for both solder pastes. Here's the solder balling test results per the IPC test method. Type 5 no clean was on that border of being unacceptable, but I would actually call that acceptable. But type 6 was certainly unacceptable across the board for both the no clean and the water soluble pastes. And here's some pictures showing those results. So you've got type 3 and for both solder paste, very little solder balling. Both of these are near preferred. And then with the type 6, this is definitely unacceptable. You've got rings of solder balls and then even clumps of solder balls here on the water soluble type 6. Here's the solder paste print data. So here we have transfer efficiency percentage, and then across the x-axis we've got the different area ratios, 0.30 ranging up to 0.50 area ratio. No clean is on the left, water soluble solder paste is on the right. The different colored boxes correspond to the different types of solder powder. I highlighted a couple of data points here just to make a point on this chart. The type 6 solder powder is shown in purple here, and for these very low area ratios with the no clean solder paste, type 6 did not give as high a transfer efficiency as the type 3 or 4 or 5, which is kind of interesting. I mean, if you were actually printing through these types of area ratios, which are extremely small, you would probably want to use type 6 solder paste. But in this case, it did not print as well as the other types of solder paste. The same thing's true over here for the water soluble with the 0.45 and 0.50 area ratio patterns. The purple box here, the type 6, is the lowest transfer efficiency, lower than the type 3 through type 5 solder pastes, which is kind of interesting and the opposite of what we would expect. Here's the same data shown as smooth curves. So for the no clean, you've got the blue curve is type 3, the red curve is type 4, the purple curve is actually the type 6, and the green curve here is the type 5. So the type 5 gave higher transfer efficiencies than all the other solder pastes. And then for the water soluble, the same thing is true. The green curve is the highest transfer efficiency, followed by the type 3, and then the type 4 and the type 6 was the lowest actually for these two area ratios. From that data, I derived some minimum area ratios for stencil design based on solder powder type. So here we have the solder powder size, type 3 through 6. Here's the minimum area ratios for the no clean paste and for the water soluble solder paste based on this particular test board and our testing in our lab with our printer and so forth. So with type 3 solder paste, we'd recommend minimum area ratios of 0.60 for both kinds of solder paste. For type 4, the minimum no clean would be 0.55 area ratio, and the minimum water soluble would be 0.60. But the type 3 and type 4 water soluble solder paste printed very similarly. There wasn't enough of a difference to actually drop this recommended area ratio. Type 5, however, showed a drop for both, 0.50 and 0.55 for these two solder pastes. And type 6, of course, didn't follow the normal printing trend that we saw with the other pastes, so more work would be needed here to establish sort of a print rule or print trends for the type 6 solder pastes. Here's the print and pause data for these solder pastes. This is for the no clean. Again, we have transfer efficiency on the y-axis. Different types of solder powder size are shown here, type 3, 4, 5, and 6. And then at the bottom, we've got the different times on the printer. So time 0, after 1 hour, 2 hours, 4 hours, 8 hours, and 24 hours. So you can see a trend here, like the no clean printed pretty consistently up to time 8 hours, and then there was a drop in transfer efficiency at 24 hours. Same thing is basically true for the type 4 solder paste, a bigger drop down to 24 hours, and for the type 5, an even bigger drop down to 24 hours, and the type 6 showed an even bigger drop. Here's the water soluble data. Same kind of trend is shown here, like it's pretty flat, a little increase in transfer efficiency, then a drop at 24 hours. From time 0 to time 1, there's an increase, and then a drop at 24 hours. Same thing for the type 5, and then a drop at 24 hours, and for the type 6, a drop between 8 and 24 hours. Here are the transfer efficiency drops from 8 hours to 24 hours for these types of solder paste. So for the no clean, for type 3, it was 8% drop, and then that went up to 10, 18, and even 25% drop for type 6. So for the no clean, that shows that no clean is definitely reacting with the air, thickening up or skinning over in the stencil, and is not releasing it as well for the smaller solder powder sizes for that last pause in the printing. The water soluble, however, showed very consistent performance regardless of solder powder size. So you've got 5s going to 8 and 6 here. So that transfer efficiency drop was pretty consistent. So it was not as affected as the no clean by this long pause in printability, which just shows that this water soluble is a little more stable and is kind of ignores solder powder size with respect to its printing and stability. Here's the solder paste reflow data. Here's the wetting data for these solder pastes. This is wetting or spread percentage. Higher numbers are better in this test. And here's type 3 through type 6. The no clean started at about 72, 75. Type 5 actually wetted a little better, like 88, and then Type 6 went back down to 70. So the no cleans, generally speaking, are pretty flat. The wetting didn't change much with powder size. The water soluble, however, started off near 100, dropped down to 90 for Type 4, 70 for Type 5, and then held a little under 70 for Type 6. So the water soluble definitely dropped in terms of wetting or spread with smaller powder sizes, which indicates that a lot of that activity is being taken up by the powder surface area rather than by the board surface itself. And so the wetting or spread, it didn't spread quite as far as you would expect, just because of those smaller solder powder sizes were reacting more aggressively with the water soluble flux. So here's some pictures of those wetting or spread patterns. The water soluble Type 3 was near 100%. You can see these are completely smooth lines. There's no breaks in the line, so that's what a 100% pattern looks like. And here's the Type 6 for comparison. There's a lot of breaks in the line. They're a little bit hard to see, but basically to calculate wetting percentage, we count the number of breaks, then divide by the possible opportunities for breaks, and then generate our wetting percentage. Here's solder balling performance. So we ranked solder balling performance on our test board using these three categories. Overprint with 0 solder balls, that's the largest overprint with 0 solder balls, the largest overprint with less than 5, and the largest overprint with less than 10. I'm not going to talk much about these numbers. Let's just say that 1250 is the highest possible number you could get, and that's ideal performance. But the pictures, I think, show it off a little bit better. Both of the Type 3s had pretty good, very low solder balling. The Type 4s, there's a little more solder balling going on with the no clean than with the water soluble. The Type 5 with the no clean, you can see rings of solder balls, whereas the Type 5 water soluble is not showing rings yet. But with the Type 6, both of them have complete rings, very thick rings of solder balling. So that's definitely not ideal performance. Here's the graping results for each solder paste. The graping percentage is shown here on the y-axis, and then we've got Type 3 through Type 6. In this case, 0 graping would be the ideal performance. Obviously, we didn't get 0 graping, but the numbers are very consistent. The no clean and the water soluble gave pretty identical performance for each type of solder powder until we hit Type 6. But they're both so high with Type 6, they're both like unacceptable levels of graping. And this is what the water soluble Type 6 graping pattern looked like. Almost all these deposits have graping showing. So in general, you can see an increase in graping with decreasing solder powder size, as we would expect, because the smaller solder powder size is going to react more with the air during reflow, and it's going to cause oxidation on that solder powder particles and prevent them from coalescing or combining together into a smooth deposit. Here's the voiding data for these solder pastes. So here's void area percentage on that QFN thermal pad. The different types of solder powder are shown across the x-axis. This is for the no clean. All these box plots are pretty much identical. If you look at the connecting letters report, that shows that these are all statistically similar levels of voiding, ranging between 12.5 and about 13.3. So no clean solder paste was unaffected by powder size in terms of voiding. The water soluble, however, showed some effects. Voiding it went up with decreasing powder size, and it went up quite a bit. If you look at the connecting letters report, all these levels of voiding are statistically different from each other. So the Type 3 gave the lowest voiding at 13%, and that went up to 20, 34, and then even as high as 41% void area with Type 6. So some solder pastes voiding behavior is affected by powder size, and other solder pastes are not affected by powder size in terms of voiding. Here's the stability data for the solder paste. Here's tack force over time. So on the left we have the no clean, on the right we have the water soluble. Tack force is shown on the y-axis, and then the different times that we held the tack force coupons are the different colored bars. 0 hours, 24, 48, and 72 hours is this yellow bar on the right. So generally speaking, you see the tack force kind of climb a little bit and then drop at 72 hours. And then it kind of climbs and then drops. And then it's sort of flat for Type 5 and drops, and it sort of just drops a little bit for Type 6. The water soluble showed similar performance for the Type 3 and Type 4. The Type 5 jumps a little bit at 24, but it flattened out with 48 and 72. And then for Type 6, it's kind of jumps a little, drops and jumps again. And that's because these measurements have a bit of error in them. So we're just looking for kind of general trends here. So generally speaking, it looks like the tack force overall is a little higher for type 5 and type 6 solder pastes. And that may be due to the fact that there's more flux there. The flux is the tacky part of that equation. But also you can see as hold time progresses, tack force tends to drop off, as you would expect. Because you've got air reacting with the solder powder, the flux then reacting with that oxide on the solder powder, and then that tends to consume some of the activity, and the flux is losing some solvent. And most fluxes tend to lose tack over time. Here's tack force after heat aging. So we took the solder paste and baked them in the oven and then did testing on them. So you've got the no clean fresh, and then the heat aged no clean is the dark brown bar. The water soluble fresh is light blue, and after heat aging is the dark blue bar. And you can see there's a drop in tack force with heat aging, generally speaking, for type 3. And then for the type 4 water soluble, there's a drop. For type 5, this is pretty flat, and type 6, there was actually an increase in tack force with heat aging, as well as with the water soluble, a slight increase. And generally speaking, the tack force went up again with decreasing powder size. Here's the viscosity before and after heat aging of the pastes. So the original fresh no clean viscosity is shown down here in the lighter amber curve. The darker brown curve is after heat aging. So you can see a slight jump in viscosity with type 3 and type 4, and a big jump with type 5 and type 6. So definitely the viscosity increased more with smaller solder powder sizes with this forced aging test. Now with the water soluble, it was very flat in terms of viscosity, and it still remained flat, but overall all the solder pastes, all the water solubles jumped up in viscosity so high it was almost off the chart in terms of the ability of our instrument to measure it. So all of these solder pastes were so thick they really weren't even printable anymore. So we didn't continue doing any print testing with the water soluble solder paste after this point. Here's the IPC solder balling after heat aging. You've got the no clean on the left and the water soluble on the right. If you remember with the fresh solder pastes, type 5 failed with the water soluble for after 4 hours, and then type 6 failed across the board. Well, now we've got type 4 failing with the water soluble that's been heat aged. So it's been forced to have some shelf life, and you've got some more solder balling going on. And then the type 5 no clean is now unacceptable, as well as the water soluble. And so that's different than what we saw when they were fresh as well. And then the type 6, of course, is unacceptable across the board. So this shows that as these solder pastes with smaller powder sizes sit throughout their shelf life, they're going to have worse performance. They're going to degrade faster in performance than the larger solder powder sizes. So the shelf life might be adjusted on some solder paste based on these type of results. Here's the print testing after heat aging for the no clean only. So here you've got the no clean fresh curves and the no clean heat age curves. These are pretty similar in terms of printability. The transfer efficiencies are pretty similar. The only major difference is that the type 6, this purple curve, kind of rose up and reestablished where I expected it to be. It should give you a higher transfer efficiency than the other pastes, generally speaking. So heat aging this no clean definitely helped reestablish that normal trend, which is unexpected. Normally I would think heat aging would just degrade print performance entirely, but for the no clean it seemed to do okay. Here's wetting after a 24-hour hold. We had the boards sitting open to the air for 24 hours, then we reflowed them, and then also with the heat aged solder paste. So you got no clean fresh, then the heat aged or the 24-hour hold no clean with the brown bar, and then the heat aged no clean with the hollow brown bar. And then the water soluble fresh is the light blue bar, and the dark blue is the 24-hour hold water soluble. So generally speaking, you got a drop here in wetting. From the 24-hour hold down to the heat aged, and the same thing's true for the water soluble. 24-hour hold dropped wetting a little bit for type 3, but type 4 pretty much flat. All three of the no cleans looked the same. Both of the water soluble tests looked the same, and then you get a drop again in the no clean, another drop again in the no clean with type 5 and type 6, and the biggest drop is seen with this type 6, with 24-hour hold and then heat aged. And then the water soluble just had a small drop with 24-hour hold here. So the water soluble was less affected by the 24-hour hold than the no clean. No clean was definitely more affected by that. And then heat aging really had a damaging effect on that no clean. Like at the end of its shelf life, wettability is not going to be as good as when it's fresh. I always like to say that, solder paste is best when it's freshly made. It never improves with age, it only gets worse with age. Here's solder balling after 24-hour hold and heat aging. I'm going to just briefly overview this. So these at the top row is all the fresh solder paste, solder balling performance on our test board. The 24-hour holds are shown here in the middle row, and then the bottom row shows the heat aged no clean solder pastes. We couldn't print the water solubles, so we did not measure that for those water solubles after heat aging. So what you've got here is, let's say type 4. You've got very little solder balling here, fresh. After 24-hour hold, there's more solder balling, and after heat aging, there's actually quite a bit of solder balling. It's just hard to see. And then type 5, you've got quite a bit of solder balling. It's a little worse with 24-hour hold, and it's about the same with heat-aged solder paste. And then the type 6s just look pretty terrible across the board. The water solubles, 24-hour hold didn't affect solder balling much at all. These are pretty clean. There's very little solder balling going on in these for both type 4 and type 5 pastes. Here's graping after 24-hour hold and heat aging. Again, you've got graping percentage here on the y-axis. And then the no clean fresh is this yellowish bar. The 24-hour hold is the dark brown, and the hollow brown is the heat aged. And then the water soluble fresh is light blue, and then the dark blue is the 24-hour hold water soluble. That graping performance is pretty flat for all these types of solder paste. So graping really wasn't affected by 24-hour hold or by heat aging, which is surprising. I would assume graping would get worse with 24-hour air exposure and with heat aging, but it just didn't. So there's other things that are taken over with this graping potential. So here's a summary and conclusions on all of this data. So here are all the tests that we ran on the left side, the different types of solder powder, type 3 through type 6. So for slump and solder balling, we've got good performance or acceptable performance for type 3 through type 5, but type 6 was unacceptable. The printing AR limits range from 0.60 with type 3 to 0.55 to 0.60 for type 4, and for type 5, 0.50 to 0.55. And then for type 6, we'd have to do more work to really refine that recommendation. Print and pause testing showed good performance for type 3 through type 5, and type 6 was not so good. In terms of wetting, all the solder paste wetted acceptably. Solder balling or pullback testing, graping testing were good, type 3 through type 5, but for type 6 was unacceptable. Voiding behavior was pretty good for type 3 through type 5, but for type 6, the water soluble was not okay. It was the highest level of voiding that we saw. And then in terms of stability or heat age performance, type 3 and type 4 did okay in both those tests. Type 5 would definitely have a shorter life than the other types of solder powder, and type 6 was just unacceptable. Now I will say that these solder pastes that we used are not normally made with type 6 solder powder. Type 6 solder powder is sort of a different animal, and it's used for different type of applications than normal surface mount application. And so type 6 solder pastes have to be formulated specifically for use with that size of solder powder. I included it with these solder pastes just to show you what the extreme potential negative effects would be with standard surface mount solder pastes if they used type 6 solder powder. So we definitely saw that solder powder size affected performance of the solder pastes. The positive effects of the smaller solder powder size were the ability to print through smaller area ratios and also an increase in transfer efficiency. And then voiding we saw was decreased with smaller solder powder sizes with other solder pastes from other studies that we've done previously. The negative effects were slump performance, solder balling, print and pause testing, graping, voiding in this study with the water soluble got worse with decreasing powder size, and shelf life would be affected by smaller solder powder size. The good news is that when we formulate solder pastes, we formulate them with the intent of using them with certain solder powder sizes, and we can turn some of these negative effects into positives by changing formulas appropriately. Thank you for your time and your attention. If you have any questions, please contact me at the email address shown here. Again, I appreciate it. Have a great day.